Hello, I'm Zhu Yang from Department of Electrical Engineer, Datong University. And today I would like to introduce the fundamental of optoelectronics. And in this section, I will divide to 4 parts. The first part we will talk about the sun, the light. And the second part, I will talk about the optical process in material. And the third one is the material for solar cell, which one is the best one, and the operation principle of solar cell. Sun provides the energy to Earth. And before we talk about the solar cell, we have to understand the original of the sun. The sun energy delivered to the Earth. Every day they will give the 340 watt per meter square, but more than 30% the sunlight will refract into the space, and the Earth will absorb about 163 watt per meter square. But the sun of the light will refraction or absorbed by the Earth to give our energy or our life. So the sun energy can transfer to the heat or to the electrical power. So people design a machine to translate the sunlight to the hot water, or you can use the solar module translate the light to the electrical power. This very beautiful picture from Taiwan, we call that is the Taipei Energy Hill. This park provides more than 2 center watt per day for Taipei. So sun energy is very useful for our people. But before to use this, we have to know some fundamental of the sun. So this transparency talk about what is the sunlight. Light is a EM wave. It means the electrical magnetic wave. So if we want to know the light property, we can use the frequency. The unit is hertz. Or use the wavelengths. The unit is nanometer. Or we can use the sun energy. It's the electric volt or joule. And from this transparency, we can see this area is the wavelengths of the sun. We can use wavelengths to call the energy of the sun, or we can use the energy. We can transfer to the energy how much the electron volt of the sun. For example, if we want to know the energy of the visible wavelengths, the energy is between the 1.5 to 3 electron volt, and the wavelength is from the 400 nanometer to 700 nanometer. So this transparency talk about the sun. This area is the wavelength of the sun. So the longer wavelengths or the short wavelengths, it means the lower energy and the higher energy. And our eyes can see the light just this few area. We call it the visible region. And this part is the infrared. This part is the UV. And we can use the frequency to talk about the sun energy. So the visible region is about 10 to 14 hertz. And we can use the last one. We can use the temperature to show the sun energy. So we heat the material to about 6,000 degrees is equal to the sun energy. So this solar radiation spectrum, it shows the whole energy of the sun. So this area is the high energy, and this area is the visible region, and here is the infrared. So this sun from the sun to this light from the sun to Earth, we can use the whole sun energy, but the atmosphere will absorption or reflection some energy, like this area and this area, okay, by the water or the atmosphere material or some particle scattering. And so in the Earth we got the energy just the red area. So another way to talk about the solar energy, we use the AM number. It means the air mass M. For example, if you in the space, the out of the atmosphere, we call it the AM0. And in the Earth's surface, we usually use the AM 1.5 for the standard, because at this AM 1.5 equal to 1000 watt per meter square. And what is the AM value? This AM value is equal to the H per H0. H0 is the thickness of the atmosphere, and H height is the distance from the Earth to the space. So H divide H0, we call that M. So you can check your location, you can calculate the M value, and then you can use this value to calculate the light intensity in your position. So we can use this method to calculate the whole light energy in the Earth. This one is the world map. The red area means they have a lot of sun energy, and I live in Taiwan, this area. So the daily sun is around 3 to 4 hours per day. And in your country, maybe you have 4 or 5 hours per day. It means it's very good to apply the sun energy, solar cell in your country. So not only AM value, usually we talk about the light intensity, we use the watt per meter square. And this transparency will tell you what the difference of the two different transparent distance. For the first one is the X, and the second one is a double X. And in the surface of the second one, the light intensity just 1/4 than the first one, because the light transformation is the sphere direction. So the intensity will, you go further, the intensity will decrease, but you calculate the total intensity will be the same. And so now we know the light energy or the light intensity. The next one I will talk about the optical process of the light. This transparency shows the three way of the light optical process. The first one is refraction, the second one is absorption, the third one is transmission. And refraction is the way we can see each other, because light reflection the surface, we can capture the light intensity. And the absorption means the energy will be absorbed by the material. And the transmission means the light can transparent to the material. Usually we can see the glass. The visible light can easily transparent to the glass, transmit to the glass. But if you got a glass with the red paper, then the glass surface will become red. So you see the red light by the reflection. You cannot see the blue or green. And these three processes are very important for the solar cell. So what is absorption process? We can use this cartoon to introduce it. And this is the atomic orbital. And an electron is in the ground state. So that is a low energy. And a light irradiates to the atom. And we call that we use the name is the photon. It's the particle wave of the light. And if the energy is equal to the energy different from the ground state and excited state, the light will be absorbed by this electron. Then the electron will excited to the excited state. It's a higher energy state. So we got the active electron. It have energy. If we can storage this electron to the battery, then we got the sunlight. But after a very short time, the electron will recombine to the ground state, and then the light will return to the photon. Then we got the photon. So this picture, this process, we call that is the luminescence process. So that is the light emit diode. It's LED like this picture. So if we want to build up a solar cell, then we have to design a structure to collect the electron before they got the luminescence process. That is the idea to design the solar module. And the absorption process will create the electron hole pair. What is electron hole pair? This figure is the Venn diagram of semiconductor. The blue one is the conductor band, and the gray one is the valence band. So in this, the vertical axis is mean the energy. It's mean the energy. So if we incident a photon to the semiconductor, then the electron will excited to the conduction band. If the energy of the light equal or larger than the energy band gap of the material. So we got an electron in the conduction band and a hole in the valence band. So here we got a hole. Here we got an electron. So we call that electron and hole is the electron hole pair. Electron hole pair. And this electron, the energy of the electron hole pair is depend on the light energy. If the light energy lower than the band gap, like this one, lower than band gap energy, the light will not be absorbed. It will transmit to the semiconductor. So how to choose a material for the solar cell? We have to choose the nice band gap. It's easy to capture all the sun energy. It means we have to choose a material band gap very low. But if you choose the band gap very low, the electron hole pair will show up in the surface, not in the whole material. So the very low band gap is not a good way to choose the material for solar cell. In the solar cell market, we choose the band gap around about 1.0 electron volt to about 2.0 electron volt, like this area. They have several semiconductor, and we can see here is the silicon. So for silicon, the energy band gap is around 1 electron volt. It's very good for the solar system. Another one is like germanium. It's good solar material. This one is the gallium arsenic. The band gap is around 1.5 electron volt, or the cadmium telluride. So in the solar market, you can see these three different type of semiconductor for the solar cell. This figure collect the best research solar cell efficiency in the world from the Unreal Laboratory, USA. From this figure, we can see the development history of the solar cell. The first one I will talk about is the amorphous silicon. The efficiency of the amorphous silicon solar cell start from the 1%, and now is improved to the 40%. For commercial application, more than 10% efficiency is good. But the amorphous silicon have low efficiency. You can use in like a calculator. That is a low power need for this product. So if we want to for the mega energy bank, amorphous silicon is not good. So the second one is the polysilicon or multi-crystalline silicon. And in the polysilicon solar cell, now the efficiency is improved to the 23%. Is a high enough the efficiency. But this data is from the laboratory, not from the company. So if you buy a solar cell from the eBay or from the market, maybe the efficiency of that solar cell is not so high. Usually for the company, the efficiency is about 16 to 18%. If you want to find a better material for the solar cell, like gallium arsenic, the purple triangle is the gallium arsenic. You can see now this solar cell efficiency is close to 30%. It's very good, but this material is very expensive. So this solar cell just used in the universal, not in the ground. And they have another solar cell like a multi-junction solar cell. Multi-junction solar cell will have a higher efficiency. The best one here from unreal is a 47%. So half energy, you can save half energy. Is very good, but now it's not a commercial material. And this green material is a thin film solar cell. The popular is the cadmium telluride. Cadmium telluride solar cell efficiency is close to 22%. But we know cadmium telluride is not good for the environment. So the company sell the product to you. If that product is broken, the company have to buy back from you. Okay, so cadmium telluride is now not popular in the world. Another one is the CIGS here. This is the copper Indian gallium selenide, and this thin film solar cell is very easy to process. So maybe that near year this product will be popular in the world. And here is the organic solar cell. Organic solar cell is very good for the environment, but the efficiency of the organic solar cell is too low. So if you are a researcher or engineer, you want to find the new star of the solar cell, maybe you can start from the organic solar cell or dry sensitive cell. The second one, we can use the anti-reflection coating to improve the efficiency of the solar cell. This picture will show you the original of the anti-reflection. This is the incident light and the reflection light. We see these two reflection light have a path difference. If we if we control the thickness of the anti-reflection coating and make the phase of the two reflection lights is out phase, it means they will not reflection. So all the incident light will enter to the material, not reflection. So in this commercial solar module, the surface always have the anti-reflection coating. But based on the associated material, they will use the different anti-reflection coating. Not material or the thickness or the structure, and the detail of the anti-reflection we will talk in another courses. So now we know the property of the sunlight. The sunlight have energy. If the sunlight incident to the solar cell, we can produce electron hole pair. But how to get the energy from the electron hole pair? We have to see the detailed structure of the solar cell. This figure is the detailed structure of the solar cell. The first layer is the cover glass to save the solar cell module, and the second one is the transparent adhesive. The third one is the anti-reflection coating. We just talk that. And the center of the solar module is the PN junction. The red region is the N-type semiconductor. Blue region is the P-type semiconductor. These two type semiconductor, between the two type semiconductor, the yellow region is the depletion region. In this depletion region, we have a built-in electric field from the N site to the P site. So if we put an electron in this region, like here, in this region, then electric field will push this electron to the N side, like this way. If we put a positive particle, like hole, in this area, this electron field will push the positive charge go to the P side. So if we have a suitable sunlight incident to the depletion region, we can create an electron in conduction band and a hole in the valence band. Then this built-in electron field will push this electron to N and the hole to P, so we separate the electron hole pair. Then we storage this electron hole pair will storage it to a battery. Then we got this energy. But if the sunlight irradiate in this region, we call it the neutron region. Here they have no electron field. So if we in this region we can create electron and a hole. But a few minutes the electron will recombine back to the hole. So we cannot storage the electron hole pair in this region. So for the solar cell, the important structure is this area, which area have the electron field. Then we can get the sun energy. So now we know solar cell is a single p-n junction, and we have the electric field in the depletion region, this green, this yellow area. And if we have a light enter the p-n junction, and we will produce an electron hole pair in this area, and electron will go this way, and the hole will go this way. So if electron go to the N side, it means the current will go N to P. And for the positive charge go P side, it also means the current is this way. So if we shorten the p-n junction, they will have a photocurrent. And this photocurrent, the direction of the photocurrent will inverse direction for the forward bias. So this IV curve of the solar cell, this one is the standard IV curve. So the sunlight irradiates to the solar cell, this curve will shift down, change to the blue one. So this part is the photocurrent. We call that is the Schottky current. And this point we call that is the open circuit voltage. So this area is the total energy we can storage in the battery. And the detail of this part, we will use another courses to introduce it. Okay, this transparency is the specification of the PV module. This data made from the Juntong. It's another. It also belong to the Datong company. And this one is the 300 watt solar cell. we can see here is the open circuit voltage is close to 40 volt, and the current is close to 9.5 amp. So the total power equal to the current time voltage, so it's close to 319, but the spec will show you the power, the maximum power is the 300 watt. And how to calculate the 300 watt? It means that each solar cell provide 0.5 volt, and we have 6 module in one. We have 6 solar cell in one module, so the total voltage is 30 volt, because all the module is connected in series, and the current is close to 10 amp. So 30 volt times 10 amp is 300 watt. So each of the solar cell module will produce 300 watt for you. So let me end this talk. Today we know the property of the sunlight and the optical process, and then I told you how to choose the suitable material for the solar cell application, and then I told you the process, how to operation a solar cell, and then we can use the solar cell to design a energy bank or a solar system. This transparency is the PV mini grid demo site at the Datong University. We have 2 different systems. The first one is an on-grid system. Another one is a hybrid system. It means we can use that in on-grid or off-grid. The first one, the PV array connect to the DC junction box, and then connect to the PV inverter and the AC panel and the power meter, then on grid. So we take the energy directly to the CT power. And the second one is a hybrid system. We can use the battery bank to storage the energy, or for the emergency load, for the emergency condition, we can save the power in the battery, or for the light, or for the air condition, for example. So, but if the battery is full, then the power control system will send the power to the city power. So we have 2 systems, and then I will show you how to design this system. Okay, thank you.